Welcome to this explainer. Today, we're taking a seriously fascinating journey back to our closest celestial neighbor. But hey, this isn't just some boring history lesson. We're going to dive right into the breathtaking orbital mechanics, the razor-thin margins of error, and the intensely competitive modern geopolitics behind the Artemis II mission. We're going to see exactly how humanity is gearing up to leave Earth's orbit once again.
The universe is 13.8 billion years old, vast, ancient, and mostly invisible. And somewhere out there are answers to questions that keep scientists awake at night. Welcome to our channel, where we explore the darkest corners of the cosmos, the mysteries, the threats, the unknown. This is space like you've never seen it before.
Okay, let's just tackle this massive question right out of the gate. Think about it. We first landed on the moon all the way back in 1969. The astronauts of Apollo 11 squeezed into this tiny, windowless module, relying on a single computer with a maximum memory of, get this, around 64 kilobytes. To put that into perspective, the smartphone sitting in your pocket right now is literally millions of times more powerful. Yet with that super basic tech, they pulled off the impossible. So why on earth, pun intended, with all our modern advancements, did we just abandon human lunar exploration for half a century? Section 1. Return to the Moon, the 54-year hiatus. To really wrap our heads around this return, we need to look at the Artemis program itself. Artemis II is taking a crew of 4 astronauts back into deep space just to test the critical systems. Say a quick hi to the lunar surface from orbit and then come right back home. So why the big pause? Well, to answer why we stopped, we have to look at how priorities totally shifted. After the final Apollo mission, Apollo 17 back in 1972, the moon was honestly deemed by a lot of folks to be a worthless pursuit. I mean, we'd planted the flag, we brought back some cool rocks, right? Plus, those Apollo missions cost hundreds of billions of taxpayer dollars. The scientific community basically decided, okay, been there, done that, time to move on. Our focus completely shifted outward, to sending rovers to Mars and launching the Voyager probes into deep space. The moon? It was kind of just old news. Which brings us to Section 2, Apollo versus Artemis, then and now. Because the motivations and the technology, they've undergone an absolute revolution. The sheer contrast between these two eras is staggering, like night and day. The Apollo missions were essentially this huge geopolitical sprint, a Cold War space race totally driven by a need to show technological dominance. And the astronauts literally had to sit there with pen and paper, manually calculating their trajectories in real time. Can you imagine? They relied heavily on a massive ground crew, and the rockets were entirely single-use and, frankly, incredibly dangerous. Artemis, on the other hand, is built on modern AI and autonomous navigation. The Orion capsule is just packed with live computers that are constantly self-correcting its trajectory. It's built for the long haul, designed for actual sustainability. And here's another huge difference. Artemis is no longer a solo sprint. It is a massive, truly global collaboration. While NASA is leading the charge with the Orion crew capsule, it's actually attached to the European Service Module, or ESM, which is provided by the European Space Agency. And it doesn't stop there. We've got absolutely critical contributions from Canada and other international partners, too. It's a unified effort this time around, basically pooling together the absolute best technology the entire world has to offer. Section 3, hitting the null point, the physics of the journey. Because as amazing as all that modern tech is, it doesn't change the fundamental laws of physics. You see, the flight path isn't just a straight line. You can't just point a rocket at the moon, hit the gas, and hope for the best. Because everything in space is constantly moving, the spacecraft has to take this massive elliptical figure-8 path. Step 1 is pure raw brute force, hitting an escape velocity of 11.2 kilometers per second just to break free from Earth's immediate gravitational grip. Step 2 is a really delicate coast through deep space. Think of it kind of like tying a stone to a string and swinging it around, slowly letting the string out. It travels further and further until it reaches step 3, which is where lunar gravity finally takes over. Right, so the absolutely crucial milestone in this journey is what astrophysicists call the null point. This is an invisible threshold out in deep space where the gravitational pull of the Earth pulling behind the capsule perfectly matches the gravitational pull of the moon pulling in front of it. The net gravity effectively hits zero. Now, because the moon has way less mass than Earth, this point is located much closer to the moon. Once the Orion capsule crosses this exact invisible line, Earth's grip finally lets go, and the spacecraft literally begins falling toward the moon. And that brings us to the gravity slingshot. Now, the math here is terrifyingly razor thin. When they fall toward the moon, the Artemis II crew won't actually have enough fuel for a powered return trip. Yep, you heard that right. They rely entirely on this slingshot maneuver. The capsule's speed and angle must be absolutely 100% perfect. If the total energy is even slightly too high, the capsule overshoots, breaks right out of the moon's orbit, and drifts off into the endless void of deep space forever. No going back. But if the speed is too low, the capsule simply crashes right into the lunar surface. It has to be just right, a perfect Goldilocks zone, to wrap around the moon and get flung safely back toward Earth. Section 4. The re-entry window. A matter of life and death. Because assuming they totally nail that slingshot, they are about to face the single most dangerous part of the entire mission. As the Orion capsule is flung back toward us, it's accelerating the entire time. By the time it finally reaches our atmosphere, it will be hurtling at a staggering 40,000 kilometers per hour. Just let that sink in. And remember, right before they hit the atmosphere, they actually have to eject that European service module. That means they are dropping all their main fuel and propulsion. They are coming in entirely unpowered, relying completely on aerodynamics and math to survive. What's really wild is how impossibly tight their re-entry window is. To survive hitting the atmosphere at 40,000 kilometers per hour, the capsule has to enter at a very specific angle, between 5.5 and 7.5 degrees. If they come in too shallow, say less than 5.5 degrees, they will literally bounce off the Earth's atmosphere. It's like skipping a rock across a pond. They just shoot right back out into deep space with zero fuel to turn around. But if they come in too steep, greater than 7.5 degrees, it means total destruction. Coming in too steep means hitting the thicker air too fast, and man, this is where it gets incredibly violent. You know, a lot of people think spacecraft heat up just because of friction, but it's actually caused by compression. The capsule is moving so impossibly fast that it violently compresses the air directly in front of it. Just like a survivalist using a fire piston to ignite a flame by rapidly compressing air, this extreme compression heats the air to a blistering 2,800 degrees Celsius. It turns the air into a superheated plasma fireball that's going to test the absolute literal limits of the capsule's heat shield. And that 2,800-degree plasma fireball creates another terrifying side effect, the Faraday cage effect. As the plasma wraps all the way around the descending capsule, it creates a solid barrier of charged ions. This plasma sheath acts exactly like a Faraday cage, which means electromagnetic waves cannot penetrate it at all. So for several agonizing minutes, ground control will lose all radio communication and data signals from the crew. Dead silence. The astronauts are completely on their own inside a literal fireball, relying purely on the capsule's automated systems to keep them alive. Section 5. Next stop, Mars, the ultimate goal. So, with all this astronomical risk, the null points, the high-speed slingshots, the 2,800-degree plasma fireballs, what is the grand ultimate goal here? Why risk it? To understand why, we have to look at a timeline of recent discoveries. After the 1990s, when American lunar scans first hinted at some strange anomalies, the real game-changer happened in 2008. That's when India's highly successful Chandrayaan-1 mission definitively detected water molecules on the lunar surface. Suddenly, the moon wasn't just a dead, dusty rock anymore. Fast forward to 2024, and China's Chang'e 6 mission successfully returned soil samples specifically from the moon's south pole. That's a region in permanent shadow where vast amounts of ice are believed to be hidden. So the absolutely crucial point here is water. Think about it. If we can mine lunar ice, we don't just have drinking water for astronauts. We can actually split that H2O into oxygen for breathing, and even more importantly, into liquid hydrogen and liquid oxygen to use as rocket fuel. The moon instantly transforms from a barren wasteland into a vital orbital gas station. It means we can build a sustainable lunar space station, refuel our rockets outside of Earth's massive gravity well, and use the moon as a necessary stepping stone to reach our next destination, Mars. And obviously, this has ignited a brand new space rush. We are witnessing the new geopolitics of space unfold right in front of us. It's no longer just a quick sprint to plant a flag. It's a deeply strategic race to claim valuable lunar resources. Much like the scramble post-World War II to establish territories and research stations down in Antarctica, the world's superpowers, including the US, China, and India, are racing to establish dominance. Everyone wants to secure the most resource-rich zones on the lunar South Pole and essentially write the rulebook for the future of space mining. which leaves us with this incredible, mind-bending thought to ponder. As Artemis II prepares to brave the null point and test the absolute limits of human endurance and modern technology, we really aren't just repeating a 50-year-old magic trick. We are laying down the permanent infrastructure for the future. By returning to the moon to stay, are we currently witnessing the true birth of humanity as a multiplanetary species? I'll leave you to think about that one. Thanks for joining me on this explainer, and remember to keep your eyes on the stars.
The universe doesn't care about us. It never did. But we care about it. And that is what makes us extraordinary. If this video made you think, hit like, share it, and subscribe to this channel. Because the next mystery is even deeper. Until then, stay curious and keep looking up.